we're going to cover two topics. What is federated learning? And then it's not really divided into two separate blocks, but we are going to see also how to make use of federated learning using Flower, which is an open source framework that we have been developing over the last couple of years. But before starting, just very briefly about me, I'm a research scientist at Flower Labs, which is the company behind the Flower open source framework. Before that, I was at Samsung AI as a research scientist as well, and before that, I was doing my PhD at Oxford, where I was mostly working on efficient machine learning. And what does efficient machine learning meant for me in particular was how can we change the machine learning models and their algorithms so they run more efficiently, like faster or running with fewer, making things run more efficiently in the energy or memory footprint aspect side of things. Because of that, I was very interested in embedded devices, and I'm also quite keen in writing tutorials and guides to show people how to run things on devices like Raspberry Pis or Jetson devices. And this is, for example, a diagram from a blog post I wrote a month ago that you can find in Flower. I will show you the link to it later in the talk. So before we jump into it, I just want to show this quote that we're going to see it throughout this talk a couple of times, which says, federated learning takes the training to the data. Currently, it might not make complete sense, but bear with me, you will see that it makes a lot of sense very soon. Before we jump into some real-world examples, I want to ask a question. Who has heard about federated learning before? Okay, I see maybe 5 hands. Okay, that's cool. So what we're going to see now is 3 real-world examples. The first, we're going to see how federated learning makes sense in a massively distributed setting where users have an app and they are generating data, and how that app that uses a machine learning model, how we can update that machine learning model without having to collect all that private user data. Another example, we're going to see how organizations can collaborate together to federate the training of a machine learning model that is going to be better than the one they can develop on their own. And in the last example, we're going to see how even for a single large enterprise that might have different locations throughout the world, federated learning makes sense because of logistical problems, or maybe different legal frameworks in different locations. You cannot just move your data to a centralized location. So in that setting, federated learning or federated analytics makes sense as well. Let's start with the first example, which might be the one that applies to all of us in a more standard setting. And as I will make more evidently later, I'm pretty sure most of you have already used federated learning, maybe even without knowing. So let's suppose we have company A that wants to develop a food application, and this app can do all sorts of things. Like, for example, you take a picture, it tells you what's on it. It can suggest you next new recipes. Maybe it can even suggest you where to make your grocery shopping based on what you have in your fridge. In order to develop this machine learning model or machine learning models to run this application, company A might pay a reduced user group to produce this data, collect this data, and eventually train this machine learning model that can be shipped into the application. And this application can later on be shipped through standard app places like iOS App Store and so on, to thousands and maybe millions of devices. And users actually love this app. There are some users that only use certain functionalities. Some users are power users, like in this case, the person in the middle. But as time passes, it is normal that this app is going to be updated. And I'm not talking about making changes to the UI or adding new functionality. I'm talking in particular about the machine learning model that was shipped at the very beginning. So how does company A update this machine learning model? One way would be to pay another user group to collect even more data. But at this point, this might be extremely expensive or very difficult because you are not starting from scratch, you are starting from an already pretty good point. So one obvious solution would be to collect all this users' data. Some might agree to do this, but the majority wouldn't want to share, in this case, images of their food with company A, because you can see how this can go very wrong very fast. So the solution that Federated Learning brings to the table is to, instead of having to collect this data, move the data to a centralized location and do the training over there, what we do is we move the training to where the data is. In this case, what this means is that the machine learning model that was shipped in all these applications running on these personal devices, in this case, smartphones, the model can be trained or, in some instances, fine-tuned on device using the data, and in this way, the data doesn't have to leave the device. We'll see later how now these updated models on the devices can be aggregated in the company A server to generate the new update of the app. We'll see that later. Next, let's see the second example, which usually in the Federated Learning jargon, we call it cross-silo. So let's say we have now 3 companies, company A, B, C, that want to collaborate to train a machine learning model. But to make it less generic, let's say that they are hospitals. And hospitals, they have very different type of data. Tabular data from medical tests, images, x-rays, for example, 3D images from CT scans, videos from ultrasound, and so on. Some large hospitals can partner with maybe some big companies and develop their own model. But this doesn't scale up to medium-sized or small hospitals that collectively might have way more data than a single big national hospital, for example. So what you could implement with Federated Learning is, with a public health authority in your country or your region, this public entity can coordinate the training of a model for different applications across these hospitals. And again, the way this would work is that the public authority will have an initial model that might be uninitialized or might be pre-trained with some public available data. And then this model is sent to every hospital, and then the hospital, they can train it on their own local servers or their own on-premises or on the cloud, if they have this kind of partnership with AWS and so on. And this collaborative training, well, it is evident that will produce better models than what can be produced by hospitals individually, because as we all know, machine learning models are very data hungry. So the more data you can feed to them, the better. You protect patients' privacy, because you don't need to move the data to another hospital or move the data to the public entity in this case. The data doesn't have to leave the servers of the hospital. And it enables dynamic participation. And what does this mean? It means that if new hospitals want to join this federation, they can join or they can go. Some hospitals might have some modalities of data, but not all of them. So this allows for multiple models to be trained at the same time. And finally, the third example, we are not talking anymore about individual users. We are not talking about different companies. We are talking about the same company, but that is spread around the world. This can be just 2 locations, as some of our partners do, or it can be many locations across the globe. Like you can think of it of factories that are in different locations because of logistical reasons. Sometimes it's unfeasible to move the data around. One of our partners is one of the largest manufacturing companies, and you can think of that the volumes, gigabytes of data that is produced every second in factories, sensor data. There is no way you can move that data to a single place and then do machine learning. So again, moving this training to where the data is the obvious solution here. So these are the 3 examples that we see coming sooner rather than later in Federated Learning. And all these come with their own bit of small problems that they need people with different skills. Some people might be into the networking. You can see there is a lot of networking happening here. Machine learning, of course, privacy, infrastructure. So no matter which is your set of, where your skills are, no matter if you are more into engineering or more research, federated learning is something that probably you want to have in your radar for the next years. Okay, so I have given a few examples of what federated learning is. We haven't seen it in detail yet. We'll see it in a bit more detail soon. But first, I want to stop a bit and give a step back and show what the current situation of machine learning is. So the majority of the machine learning models we see these days, some of which are very popular, like stable diffusion, large language models, and so on, it seems that they have been training super large volumes of data. And if we compare that amount of data with what was used just 5 years ago in state-of-the-art machine learning models, it is true. They train in much more data, probably all the publicly available text data on the internet, for example, for LLMs. But that amount of data is really nothing compared to all the private data that is stuck in hospitals, in small and medium companies, in your lawyer's laptop, in banks. And there is a good reason why this data is not publicly available, right? It's highly sensitive. But because there is currently not a good way to make use of this data, we cannot train, for example, a super large model for predicting health problems, for example, because all this data is in hospitals. And this applies to many other domains. So repeating again the same quote I presented at the beginning, traditionally what machine learning requires you to do is to collect a lot of data, centralize it, and then you can apply all your machine learning models and training. Federated learning does exactly the opposite. You don't want to collect any data. You might coordinate how this training happens, but you push the training to where the data is. So now that we know a little bit how machine learning works, we're going to see a bit about Flower, which is a framework for federated learning, but it also allows you to do federated analytics and federated evaluation. So with federated learning and with Flower, it's a framework written purely in Python, but because federated learning, you might run it in multiple type of systems, you really need to interact with other operative systems. For example, you can have bindings to Android, iOS, C++. You can run it in settings like cross-silo, which you might have access to high-performance computing settings. So you can make use of your usual tools, maybe in Docker, even Slurm, Kubernetes, and so on. Or you might run it in cross-device settings like Raspberry Pis, smart home assistant, phones. You can do all those as well. As I said, Flower is ready for federated learning throughout multiple stages in the development process. You can develop on your laptop or your GPU cluster you might have access to in your university, for example. You can run it in simulation mode, which I'll give some details later. You can run it in non-simulation mode, which, for instance, can be done establishing a gRPC connection between clients and server. The clients might be spread around the world, for example. And Flower you can make Flower work with your favorite machine learning toolkit or your favorite data science toolkit. For example, I normally use PyTorch, weight and biases. Others like to use TensorFlow, for example, much more, and that's cool as well. Recently, I've been writing some examples with Hugging Face, which, as you all know, is one of the main repositories for state-of-the-art models in large language models, speech models, and more. And the Flower community is really growing rapidly. We have almost 100 contributors, close to 3,000 developers in our Slack that I will show you later how you can join. And there are a lot of projects that are depending on Flower. Because we really believe in the open source community, every year we organize what we call a Flower Summit, which is a 2-day event, just like this one, where we invite people from academia and industry to tell us what they are doing and what they find exciting about federated learning. One of the cool initiatives I was running this year was what we call the summer of reproducibility, which is one of the big challenges in federated learning, because it's not only machine learning, but distributed machine learning. There are stochastic elements, because you have to sample clients and things like that. Reproducing the experiments in research is super complicated. So we invited the open source community to join in the effort of reproducing some 50 papers publishing in tier 1 conferences, and the response was really huge, and we are starting to merge the first baselines. So if you are curious about it, take a look at our GitHub. Okay, but Javier, you have been telling us some examples about federated learning, but we haven't seen how it actually works. So what I'm going to show you now is the typical federated learning pipeline, which starts with a model in the server. As I said earlier, this model might be randomly initialized because you want to train it from scratch, or it might be pre-trained. So what the server does is some clients might be connected to the server because they want to participate in the training. So the server will sample some of the clients. You can sample all of them. You can sample a fraction. It really depends on your setting and what you want to do, basically. These clients that are sampled for a round of training receive a copy of the global model. Then these clients, each of these clients, here I'm showing them as smartphones, but they don't have to be a smartphone. Each of these clients will train the model using their local data. And this training actually is a standard training, like the normal training you would do in standard machine learning. After a few epochs of training, which is a hyperparameter, these models have changed and they are now different. Before they were the same, but now they are different because they have been trained or fine-tuned with different data. These models are communicated back to the server, and then one of the key stages in federated learning is defining how you aggregate these models, which means now I have n models because I have sampled n clients. How do I obtain a single model out of this? You could take the average, for example, because after all, these machine learning models are just big tensors. And in fact, this method of just taking the average, which is called Fed average, is one of the most standard ways of doing it. It's the way we are going to see it in the example, and it's one way that actually works okay in practice, but not always. Okay, so enough slides. Let's see how this actually looks in code. So the Flower API is very lightweight. If you already have your machine learning, standard machine learning code, you're training an image classifier, for example, taking that centralized or standard machine learning model and start a federation is actually pretty easy. What you need to do is to define what your client is and what your server does. And the typical Flower client only needs these 4 methods, some of which are optional. I'm going to explain what each method does briefly. So the fit method is the method that will be executed when your client receives a model from the server. And in the fit method, what you would write is, oh, I have received the parameters from the server, and now I'm going to instantiate my model. It can be Python, it can be TensorFlow, it can be Hugging Face, whatever you want. And I'm going to do some local training using my standard tools of machine learning. And then once this training has done, I will return it back to the server for aggregation. How do I define how the aggregation works? Well, that is done in the server. You choose an aggregation algorithm that we call in Flower strategies. And in this case, you can see that I decided to use a Fed average. If we move one slide further, what I'm showing here is exactly the same code, but what I've done is populate everything so it works for a PyTorch example, which I'm going to run very soon. And because this looks a bit small, I'm going to zoom in a bit. And I'll show you that here, for example, my constructor, what it does is just instantiates a model that is done in a different file. in this case, I'm instantiating a standard CNN, and then I'm just obtaining my training and test partition. Here I'm using a Torch Vision dataset, which is from PyTorch. But for example, if you work with Postgres databases or anything like that, you could create that connection to your database here and use it later in the feed method, which in the case of PyTorch, it would look like this. You receive your parameters. In set parameters, what you do is you apply those parameters, which is a NumPy array by default. That's the Flower internal is framework agnostic. Everything runs on NumPy or standard types in Python. So what you receive from the server is a NumPy array, and you can apply it to your PyTorch model, call your standard training function, and then once you have received the model, you just return it back to the server because your model has been updated. And that's pretty much it. You can, of course, the server, you can make it as complicated as you want. Your strategies are highly versatile. In this case, I'm showing you how you can parameterize it even further. For example, fraction fit controls the number of clients, the fraction of clients that are involved in your training. By default, they are going to be all of them. Here I'm just showing, I just want to sample half of them. There are a set of callbacks you can use to further customize your strategies behavior. And if you want even more customization, you can, by standard Python inheritance, you can fully customize your strategies. Okay, so I think I'm running out of time because I'm talking too much. But I'm going to show a live demo. I think there is value in showing live demos. So I'm going to do just that to show also how easy it is to run Flower. Okay, so what I have here is, this is just a quick start example in PyTorch that you can find in our GitHub repo. And, well, in Flower, we use Poetry extensively. I don't know if you know Poetry, but it's quite cool to build your Python packages. What I'm going to run here is my server, my client, another client. And in this example, what I've done is, In this example, what I've done is I'm telling the server to wait until there are 3 clients connected. So nothing is happening because only 2 clients are connected. So what I'm going to do is I'm going to launch the next client. Flower, examples, quick start PyTorch. And now that my 3 clients are ready, what my strategy is doing is sampling half of them. I have 3 clients, the half of 3, you round it, and it's 2. So this is what is happening, basically. There is a round of fit. My clients are doing local training now. Now my clients are doing a local evaluation. It's called evaluation. I'm going to show you. This is exactly the same code I showed you earlier, but I've added some printf statements. At the end of every round, you get some login on the server telling you that, actually, the study has sampled 2 clients out of n, in this case 3, and then I receive these many results. It will log you if there are any error. I'm going to start moving because I think I'm running out of time, so we'll get back to this very soon. Okay, there are some, very briefly, in flower.dev. Through flower.dev, you can find our GitHub repo. There is documentation as well. We have more than 30 examples, so I invite you to check them. Not all of them are image classification. There are many examples for different type of machine learning frameworks. Now I'm going to go a bit fast because I'm running out of time, but what I want to, the take-home message from this slide is that Flower, even though we have seen the small functionality of it, it's a proper framework. It allows you to run simulations, so that means that we are not using gRPC. It means that you can spawn clients in a resource-aware manner. You can say, this client needs 2 CPU cores and 0.25 of my GPU available memory, for example, so you can control that as well. You can write custom strategies. It's easy. There is no time for this. Simulations, we see people using it with some of their favorite tools. In my case, for example, I like to use it with Slurm and Hydra. Hydra is a configuration tool written in YAML from Meta. It's quite cool. I invite you to check it out. But federated learning is not a solved problem, and by itself, it doesn't mean, because you are taking the training to the data, it doesn't mean that it's fully private and you are ready to go. There are still some challenges, and I want to highlight a few of them. Some of the challenges is that the data on the clients is not ID, which means that some clients might have a lot of data, some clients might have very little data. And what can happen is that because one client has a lot of data, my model gets updated, taking into account much more the data of this client. And because there are a few samples on this other client, I'm not learning from this client. So what can happen is that some bias issues can arise very, very quickly. It's massively distributed in the cross-device setting. So how do we handle, for example, all the incoming traffic? Because now the traffic that my server for aggregation is going to receive is going to be machine learning models or parts of machine learning models. This can be megabytes, can be gigabytes. Is my infrastructure ready for that? What if I don't want to saturate the communication channels? How can I compress these models that now I need to move around to my clients? Not all devices are the same. Like, I have a relatively good iPhone, but some other user might have a much more less capable phone. So am I going to give them a different user experience because they have less memory, for example? My model is not going to be able to train in that device because it has less memory. That wouldn't be fair, for example. And then privacy, security, and trust. A lot of people is going to be involved in the training. What if there is a bad actor that, instead of just letting the application train the model, is injecting some malicious data to confuse the model that later on is going to be sent back to the server for aggregation, and that's going to potentially break the model for everyone. Trust. We saw the example with hospitals. Can we guarantee that all hospitals trust each other? What about the central public health authority? Can we trust it, for example? Are we sure that they are not going to go sell the model to somebody else, for example? So all these kind of things are very relevant for federated learning. There are some keywords that you might have heard about, which is differentiable privacy, secure aggregation, encrypted arithmetic, which is something relevant for, I think in the next talk is going to be homomorphic encryption. So this is also quite relevant for federated learning. And now I'm finishing. This is the quote we started at the beginning. I hope now you more or less understand what it meant, what it means. I invite you to check the website. We have documentation, talks, events, lots of things, lots of materials. If you want to take our GitHub, this is the quickest way to find it. We have examples, really good examples. This one on the right is, on the left is one I wrote last week to run OpenAI model on the Raspberry Pis. If you have one, if not, you can write on GPU. Step-by-step tutorials on Colab, if you are more familiar, you prefer working with Colab, and long tutorials on YouTube. And this is everything. I'm sorry for the extra 5 minutes. Thank you.
Thanks a million. That was actually really interesting. I was actually just kind of wondering, and it was kind of covered in your last point, on the challenges, just around like, is there anything in Flower or kind of like a methodology for federated learning in general to handle like maybe users using an app or a hospital who just has a poor data process that like handles poor quality data? So like if someone's just saying, yes, this worked to everything, and it's obviously feeding back into your aggregated model, but like, since you're taking the model to the data, you can't really assess, oh, why is it predicting this right, wrong? You know what I mean?
Yes, very good point. This is actually one of the things that gets more difficult because you are doing federation. For example, if you centralize all your data, you can preprocess your data, you can, there is one weird outlier, you can throw it away. Now you can do it, for example, at the hospital level, let's say. Many hospitals, surprisingly, they have data science teams. So they can do some of this, but there has to be some coordination. For example, one of our ongoing collaborations with some hospitals, tell us that, oh, this hospital has this protocol to do X-ray images, and this hospital has a different protocol. So the images, they all look like X-rays, but some of them have some metadata at the top, some don't. So I think currently there is not a perfect solution for everything. Usually you want to bring people into the same room and decide these things. But it gets much more difficult when we are not talking about doing federation between organizations, but between regular users. That gets much more complicated. And that's why that I think it's going to take a little bit longer to come.
I have a million questions, but I'm sure I can catch you afterwards. So one is, you mentioned that the training happens on the devices, then the weights are gathered, sent back to the central scheduler or whatever, and then averaged out, and then whatever way you're using to send requests or to use that to make that model usable is going to be put somewhere else. Have you tried the reverse, where when you train the model, you send the weights back, you aggregate them to get the best overall model? Are you able to send those weights back into the device and then, say, for example, serve the user from the device via Flower? Is that even possible, or does that make sense?
I understand the second one, because that's what we do. I'm not sure if I understood the first scenario you mentioned.
Okay, so you have, the training is happening in the device.
Yes.
You collect the weights back once the training ends. You send it back to wherever the Flower server is being hosted at. You average all those weights out, and then say those weights, I put them in a fast API server, and then they communicate, the model communicates via HTTP with the application,
for example,
from AWS or something like that.
Yeah, for example.
Can the reverse happen, where I send the weights back into the average weights back into the device,
to the client directly,
to the client side, and then they're served from there, or is that a ridiculous use case from like lowering latency and so on?
I think this is more like an infrastructure-related question. I think to me both will work equally well. I think. Okay. I mean, I'm not so familiar with what's the more professional solution. For example, when you do training, what you do is your client trains, client sends the weights back to the server, and then the server will aggregate them and then redistribute them to the clients directly. So, but for example, if there is an app, like in the first example we saw, maybe this app is not going to be, injected into the user. So there has to be somewhere in the cloud that eventually when the user says, oh yeah, let me update, it will be pulled, like from an S3 or something, I think.
Okay. So this is assuming that the model is living inside the client. Like say, for example, the application in my mobile phone.
The model lives in the client, yes.
Got it, okay.
Yeah.
Okay, perfect, thank you.
Yeah.
The last question, quickly. Okay, thank you very much.
So you talked about training between different organizations, like different hospitals or end user devices. Is this also useful for training inside or within an organization, but between different data centers? Is it considered for that, and how useful is it for that scenario?
Yeah, actually, that's good point. That was the third example I tried to present at the very beginning. So sometimes you have big companies that they have, offices, or they collect data, their own data, on different locations. And because of legal reasons or logistic reasons, you cannot just move it from the different locations into a single one. So this makes a lot of sense. And actually, some of our partners have this problem. So they do this. Yeah.
And with that question, we will be closing off this session. Thank you very much, Javier.
Thank you.